morning, everybody. So we are now going and moving out from the theory part to more practical things. So we will focus on crystals. The first lecture is about that, and the second lecture will be that we will have a walk through how we do the work with the computer. And then you will have this handout to yourself, and we organize it so that if you like, you can get, if you don't have these programs, you can get them from us. So you can then do it at home with your own computer. And it's a Windows-based, it has two versions, Windows and Mac. The Windows version is easy to install, it's easy to do. But the first thing we will discuss about the crystals, because remember, when we started the whole thing, that the most important thing is the crystal. So if we don't get the crystal, we don't get anything. And now the idea will briefly go through what is a crystal and how to grow that. There are many methods. This is really an important thing to do this, that if some method doesn't work, then you can use another. There are some tricks and treats and things like this for doing this. So that is experimental work. So until now, we have been dealing with theory in a very, let's say, surface level, trying to explain the diffraction and all these kind of origin X-rays and so on and so on. But now we go really to more practical thing. So we need the crystal. So what is a crystal? In general terms, crystal is our target. Remember, this is single crystal X-ray diffraction or crystallography, and we can't really do anything if it's non-crystalline. We can have a powder or a single crystal, but the information we get from these two things are different. With the powder, you can see if it's crystalline material, and you can get some information like unit cell from a powder pattern, but for the molecular structure or atomic resolution, you need a single crystal. And that's now our target. So, surprisingly, this first sentence is true. So crystallization is the often most difficult and time-demanding step in there. And you will soon see this. When we get through this, when I will show you how much does it take time to get an X-ray structure done, you will be surprised. Because most of the time, it might be so that 99% of the time you stay in the lab, making a compound and crystallizing it, or complex, or whatever entity you might have. And that's the point. And why it's so? I've emphasized it many times, because when the diffraction happens from the atom cloud or electrons of the atoms in the structure, how they are organized. So the point in there is, what is crystallization? Crystallization is that you let nature organize your object, your molecules, in perfect 3D orientation. And if this happens, then the diffraction happens. But if it doesn't, then there is no diffraction, there is no information. And that's the idea. So the quality of the crystal determines the quality of the data, which determines the quality of your structure. And if the data is bad, the structure is bad, or even in this case, that you can't even get the structure. And it can be very annoying. So the idea is that the optimum size nowadays is around 0.1 millimeter. So it's so small that you cannot see it. So you have to use microscope. And here you have seen these images that they are different crystals from microscopic images of different crystals. And the point in there is that we aim the best for our purposes would be sphere. But it's very difficult to grow good spherical single crystals. This is very unique. And normally that's not the case. But then the next one would be cube. Because it's in the same direction, always the same shape. Why is this? It is that because we hit X-rays with it, then if it's like a thin, like my finger, say the absorption in this direction is much less than in this direction. So the idea is that if it's a sphere or cube, then the absorption in all these directions is the same. So that's the idea. So we aim to have it. And we are in difficulties if it's a very thin plate. So let's say like my hand or even more, then one dimension is very thin. Because what it means, what we need the volume. We need a certain amount of atoms or molecules in that crystal in order the diffraction to happen. And if we have a very thin crystal, then that direction there is not that much information coming because there are not that much atoms in that sense. But that's the idea. And now, this is a very important. Quite often, not always, the crystals look nice. The looking nice means regular faces and edges. Like here, if you look for these things now, they look really like a nice rhomboid kind of a thing. And this is normally a visual information that this crystal might be good. But just the looks doesn't tell. It's the same as with the persons. Person might be nice looking, but not a nice person. It's the same thing, a crystal. And now we can go to, so this actually is a little bit old, we can go to 10 micron relatively easily. 10 micron is 0.01 millimeters. And they are extremely small. And this is for the current instrumentation. The instruments are so powerful that we can study very small crystals. If you have a too large crystal, so let's say that you have a crystal like this would be 1 millimeter. So you will not be able to use this 1 millimeter crystal, but you can cut crystals. So like you cut bread or anything, you can cut crystals also. And then you get the correct size for this. But the point is that if they grow naturally on this size, then we are happy and we can just do this and pick the crystals. And the idea is that, of course, the more heavier elements they are, the more there is electrons, and if it's well ordered, the more it diffracts. What it means that we can, with the heavier elements like polyoxymetallites or something that have molybdenum or tungsten, then a very tiny crystal will be. Now, general considerations. Factors which are happening during crystal growth. So the point is that it doesn't appear from air. We have to grow the crystal. Typically we have to tell our molecule to crystallize. And the process is called the crystal growth. And that is what has a big impact. So how this happens, nobody actually really knows. It's really difficult to tell how the molecules are coming and what is the actual idea of how they start growing. This is completely, I would say, completely unknown. So it's really a mystery still why it happens. There is more and more information coming and also knowledge, and maybe we will have more information. It would be really crucial information to know what there is happening during that time. So one of the things when we are normally working with molecular systems, that you have to solubilize them in some solvent. So solubility of the compound is important. So of course you can't grow crystal from a material which is not soluble. If it's not crystalline or single crystal by itself, then you probably, we discussed about the moss yesterday, we traveled energy talk. If you dissolve it in water, it decomposes. So you cannot, unless you have a system that you cannot dissolve it. But then it means that it has to be single crystalline by itself. Then it's fine. So when we get our target, it doesn't matter how we get it. And sometimes it is a really complicated thing. So the idea is that we can consider in our vessel, you will soon see this kind of a thing, it could be a tube or a flask or whatever. We call it, or we name some of the points where the crystal starts to grow, we call them nucleation sites. So somehow a group of molecules will go into one place and they organize. It's in a very tiny tens of molecules or so, and then it starts to grow from there. And then that is, we call it the nucleation site. And then that's the idea, and then mechanical shaking. So this is easy to understand also, because their process is very subtle. It should be, we should let it happen in peace. But if you shake the thing, it doesn't happen. The shaking is bad. It destroys the process, because it's like shaking all the time, these things. If you get something upon shaking, they will be very tiny. But the idea they might be too small for it. So that's the idea. The time, this is of essence. So the point is really that you never can, in advance, never tell how long does it take. It can take from some seconds to months. And you can never know that in advance. So that is a really complicated thing for us. That, for example, a PhD student has a project to crystallize something. And then you wait 9 months and nothing comes out. So it's a really complicated. I can tell you a short story about this length of crystallization. I had a postdoc researcher from Italy, and he was doing this thing. So he prepared, there was a uranium uranyl complexes, a very heavy metal, and then an organic ligand in their metal complex. And he wanted to have the structure of these things. So he prepared 90 samples, 90 different experiments in his first 2 weeks. Then he was staying 3 months and waited 3 months, nothing, absolutely nothing. So he went away. I thought, oh, this is maybe this is gone, all the work is like in vain. But then we decided, okay, that leave it in the hood, leave it there standing, and we left it there. And then the same hood was taken into use by a master student 6 months later. And the student came to me and says, there somebody has left a lot of tubes there hanging in the hood. That what shall I do? Shall I put it in a pin? And then I first said yes, okay, but then I said no. I remember that this was left by this Italian guy in there. I said, don't throw them away. I will check them. And it turned out to be, we got 30 X-ray structures out of it. And it took 9 months. And nobody knew what was happening. And that's really that is really the difficulty with this. It's like both plus and minus, that you can just leave them there and then go occasionally and look, or then it happens by itself or it doesn't. So that's really, and then if we are lucky, we can get really this kind of a crystal. That is also quite, but this looks really strange. And sometimes, because it's difficult for you to see, there is it's like a star thing, that the tip of the star might be okay. So sometimes it's really bad looking, but it can be crystalline. It can be single crystal. So what we have to do, of course, this is a clear, all done with organic chemistry or some other things also, that if you have an impure material, the melting point of that will go down. And this means that it's impure, it's messing up. When you have crystal lattice, it's always at a higher melting point. So we have to have a pure compound, as pure compound as possible, because impure are either they don't crystallize at all, or they create a precipitate, a very tiny crystal, maybe powder, which we can do a powder diffraction, but not a single crystal, they're too small. So the idea, normally this means smaller crystals, and you might have, sometimes, if you're lucky, this means nice, that your impurity crystallizes with your compound. And then you get the structure of your compound and the impurity at the same time. But this is very rare. Typically they don't like each other, and that's the case. So the point is, when we purify, the purification of course minimizes all the other possible things what we might have in there. So we always aim as pure compounds possible. And the one that is interesting, by doing successive crystallizations like we do in organic chemistry, we'll purify the compound. So we dissolve it, crystallize fast, we get the crystalline material, we separate, we dissolve again, do the same thing repeating. In this way, typically the impurity stays in solution and we get a pure product. This is one of the easiest ways to purify materials. And that's the idea. You can do the conventional or other purification methods. So that's the idea. But the point is, what is very important, we have to know, or it's very helpful to develop a solubility profile. So the solubility profile is a very simple thing. It's just information, but where does your compound, or in which solvent your compound is soluble, completely soluble, and where it's not soluble at all, and then where intermediately soluble. So these three informations are crucial because we can then modulate this thing, because the idea of what we want to do is that our molecule will not be happy in the solution and it wants to crystallize. So we try to persuade it, and this is the way for us. We change the environment, and that's the idea. And then, of course, clean glassware is the point, because if it's not clean, that will bring impurities, and then, of course, we are in problems with this. And the idea is that when we are doing this, now depending on the amount of material you have to work with, I would say that in practice 10 milligrams is like a minimum amount which is reasonable to work with. The more you have, the better it is, because you can do simultaneous experiments. You can do one experiment and second, the third, like I told you about the Italian guy who made 90 experiments because there was enough material to do this. So that helps us because we can't be sure which of them works, so let's make many. So that's the idea. Because what we can do, we can change the conditions, and the conditions can be solvent. Select 20 solvents. Then you have a 20 experiments. Then we can use temperature, select different temperatures. We can have that in a low temperature or room temperature or elevated temperature. That's fine. Or we can use different concentrations. We can have a low concentration or high concentration. And then we have several techniques which I will teach you. So now, if you look this carefully, you can easily see it's really easy to make 100 different experiments and let them go simultaneously. But normally we don't do this. Normally we try to think in advance, develop their solubility profile, and then say, okay, my molecule has this and this kind of functional groups, or this is a metal complex and we can't dissolve it in water, so maybe it's a different solid. So thinking in advance what we have will make our life much more easier. So we aim already, like by thinking, figuring out what could be the best ways of getting the crystal. And then the solvent is the thing. We, as we spoke, 99% of our cases is though that we solubilize our target somewhere and then do something for that solvent where the target is, that it wants to come out as a single crystal. And the point is, if our target molecule is too soluble, nothing happens. It will make a class. So all the solvent evaporates and then nothing is there. And the idea is that either there is nothing or it's very tiny crystal. And then the point, avoid the solvent which make a supersaturated solution. So this is an idea that you get so high concentration at a certain temperature, and when you tap it, it will solidify. So their concentration is too high. This is rather rare, luckily rather rare situation, but can happen. Because by shaking, it will like a freeze the whole thing. But that's the idea. Supersaturated also gives too small crystals. So nucleation, this is a really abstract thing. That's the idea that we spoke about nucleus and sites. But nucleation is the phenomena where a few of these molecules meet, and then they will attract the other molecules. And that's the idea. And then we have fewer sites. So the idea, and then there will be a grow on that. It starts to grow on that part, so it can grow bigger. So if you have a lot of these nucleus and sites, then we have a lot of small crystals. But this we don't know. We don't see, we can't tell that that's a nucleus and site and that's not. It's just by chance what happens. And the idea is that in crystallization, sometimes if there is, for example, dust in the air, and this dust goes, penetrates to the solution in the technique what we are using, that might act as a nucleus and site. It might grow nice, and the dust is so small it doesn't interfere anything, but the crystals grows on it. Because then maybe there is a one dust or particle and then 10 to the power of 8 molecules. So then one dust particle doesn't make it. That's the idea. And then the mechanics, this is the shaking. This is the idea that if you do shake your material or the vessel what you're doing, mechanical disturbance will also do the same thing. Any disturbance is the idea that if it's shaking a bit, if you put it on top of a fridge, the fridge is shaking, that's bad. Normally it doesn't work well. So let the crystals grow with the minimum of disturbance. They are, I can tell you by in real life, they are so sensitive that even looking at them is not okay. So what it means, of course not true, that you just leave them. So you do it, you put it in a nice place, and then you go away. And then in the next day you come and look without touching this thing. Then look, okay, can I see anything in there? If not, go away and come back in the next day. So this kind of a thing. And sometimes it helps if you forget it. For some reason. It's quite interesting, the idea that you just leave it there and then you, hi, you left them 2 weeks ago, let's go and see what it is. Here's a crystal. So that makes, it's really a complicated thing to plan in advance, okay? Now the crystal will come on Monday at 8 o'clock in the morning. No, that doesn't work. But mechanical steering is always bad, so always avoid this. And then time, I already told you about the story, about the time. It's something also you don't know. But now when we go to the techniques, different techniques, we can modulate the time. So we have possibilities of somehow have a control for the time what is happening. And then it is of essence. So time required to obtain good quality crystals can be anything from minutes to years. And this is really true. This is not just a sentence. The idea, but if you want to have this, be patient. So if you are rushing, I already got something, and then you go and put it down, it was not good one, and then you destroy the crystals. So be patient and see them, and then remember they are very small. So we have to always look them by microscope. So that's also the idea of that. The point in there, by a rule of thumb, that if you have a test tube and then you can see crystals, they are already too big. But luckily you can cut them smaller if you're clever with this. So now we go to the techniques. So how to do this drill. These were the general things that you have to take into consideration. That's the normal work in the lab, what you do. Whatever kind of target you have, would it be purely organic, either could it be purely inorganic, there is a method also. It could be like yesterday you heard about the moths and the coughs, it's the same thing. And actually yesterday Rahul was showing one technique. This technique was used to prepare the material, but it's also a technique to crystallize, make crystals. You will see that later on. So that is the essence. It doesn't matter what you are studying, what you're doing, what's your target, but the principal idea is to be able to control what happens. And this control happens with different techniques. So the simplest, of course, what you can consider is that you take sugar and you dissolve it in water and let it stand. The water starts to evaporate, and in a certain time there will be a concentration cut or concentration limit where the sugar crystals or sugar molecules are seeing the other sugar molecules and they start forming a crystal. And then the crystals form in there. And that's the idea. It's a slow operation, it's the simplest. And now it's easy to understand the idea. Of course, the polarity makes a big difference. Do you use non-polar solvent or polar solvent? Is it an aprotic solvent and so on? You also have to think about this when you're looking at your target molecule. So if your target molecule gets got into the metal complex, for example, then you have to be sure that you will not destroy your metal complex when you are dissolving it. So that's the idea. But that's quite, I think, intuitive when you're actually working with this kind of, because if you prepare, you know already something how your target behaves. But that's the idea. Slow operation, make decent, again in here is if the concentration is too low, nothing happens. But if the concentration is too high, it comes too fast. So again in here, information or knowledge, let's say that how many milligrams of the compound dissolves in that given solvent in room temperature, for example. That's very useful information. And then when you know this, then you make a lower concentration, maybe 1/2 of it, and then let it stand, test tube or anything other, and then let it evaporate, and then look what is happening. But of course, it's easy to understand that when you have evaporation, if you don't look into it, if you forget it somewhere, it will get dry. And this is bad, because often crystals contain solvent, and if it gets dry, it cracks it destroys the crystal. So you have to, in a sense, follow the slow evaporation is a technique. You have to follow how evaporation happens. And typically, I don't have a blackboard here, but I can draw. So the actual idea is that you fill up the test tube with your solvent, and where the carbon molecule, you made a mark on the upper level of the solvent, and then you just follow. Okay, now it went 3 millimeters down, now it's 5 millimeters, half centimeter. And then you observe what is happening. This is the way to do this. And then can be saturated or nearly, it doesn't matter. So it depends on how, what is the behavior of your target molecule in there. And then you can slow it down very simply. So if it's an open tube, it goes faster. If you take a test tube and put ether in there, it goes quite fast. But what you can easily do, you just cover it with something. You can put a glass plate in there, or you can put a rubber septum in there, or anything. You can put aluminum foil and make small holes in there. All the other things, everything is allowed just to control the evaporation rate. And normally, the slower is the evaporation, the better is the result. Because then it's a slow process. It has time to find the best conditions for the crystal. And that's the idea. And now, again in here, when you do the slow evaporation, place the container in a quiet, out-of-the-way place. And let it be. But now, because it's evaporating all the time, the concentration will go higher and higher when the solvent evaporates. There will be a case when the crystallization happens, if it happens at all. But if it happens, then what you should do, now it's done, you should close the vessel and keep it, because then they are safe. Don't let it dry, because you don't know if the crystals contain solvent, and if they contain solvent, if they dry, they die. So that's also a practical thing to do. So the idea is that keep it. Now, they are crystals obtained by slow evaporation. They are there. Sometimes you have stable crystals which are stable in the air. Sometimes, especially large supramolecular or whatever structures, there's a lot of solvent. And then it will destroy immediately when you take the crystal out of the solvent. But this is the idea that if this happens, then you know, okay, my crystals are very sensitive, I will keep them in solution. There is techniques how we pick up a crystal from solution and put it in the diffractor. So now, the key success is to control the rate of the evaporation. That's it. If it's too fast, that's your, and then don't let it go to dryness. This is actually what I indicated. And the point is that in some cases, it happened many times to me too, that okay, by accident it went dry, but then the crystals had formed in the wall of the tube, and when you try to take them out, they were glued in there. When you try to take them out, they crack. So it was really frustrating. Very nice looking crystals, probably very good single crystals. When you take them out, when they dry, they die. So they crack. And that's the idea. And believe it or not, Panama tube is a very nice vessel to evaporate. It's a really thin, long tube. And when you have about 2 centimeters or 1.5 centimeters of solvent, you're compounding there, and you are doing animal research, or animal research tell you, okay, it's a pure compound, then you just let it evaporate in an animal tube. And then look for that in an animal tube. Okay, now the crystal is there, very fine. Then you can even crack the animal tube and take the crystal out. So this is a very simple way, because you have done the work already, then why not let it evaporate from the animal tube? That's the idea. Then the next easy way of which is more safer in certain sense, is slow cooling. So the idea is that the evaporation you have to control, you have to somehow survey that it doesn't go to dryness. But now slow cooling is a reverse technique in a sense, that now you don't evaporate the solvent, you lower the temperature of the solvent. And this is done always with a closed vessel. And then the idea, then there is no evaporation, you just close the vessel, put it there. But what you do is that you heat it out, so you look for a system that your molecule is soluble in elevated temperature, but not in low temperature, or lower temperature. So let's say that it's completely soluble at 70 degrees, but it's not soluble in room temperature. So what you simply do, you put your substance in the solvent, you heat it up to 70, then you close it, put the cork on, and let it stand. And now, upon standing in the air, depending on how large is the volume, it will cool down to the room temperature, and then the temperature gradient induces the solvent crystal growth. And that is a very nice technique in that sense that if this works, then the crystals are safely in solution already. Then you have to just pick it up from the solution. And that's the idea. So the point in there is that you can also do it in a different way, that you start from the room temperature and you put it in the deep freeze. So you go from 25 to minus 20, and then the crystals grow when you go, let's say, to minus 10. But now there is the difficulty with this. Because if you now take that tube where you crystallize the vessel to the room temperature, it will dissolve back. So what you have to do, you have to be able to separate the crystals which are formed at low temperature at low temperature, to remove the solvent. And one thing is, of course, that if the crystals are on the bottom of this thing, you just quickly remove the cold solvent and then keep the crystals in there. They might survive when they are dry, because they are soluble in the solvent, not in the air. But there are also techniques how you can actually do this in minus 10 or minus 20 or so. But this is a rather special technique. But it's possible. So it doesn't matter what is the temperature range. But you have to be able to then handle the formed crystals so that they don't dissolve back or they don't crack. So now we are going to the technique what was shown by Raul Paneria yesterday. He didn't talk about this, but this is actually, this is not the freeze-thaw system, because this is only making a vacuum inside the tube and then heat it up. Because you can do it reversed. And this is actually what happens. And this is called a hydrothermal or solvothermal method. And this hydrothermal means water, and the solvothermal means any other solvent. And it's a very simple technique, but this needs instrument. The first two ones need only a glass tube, for example. It doesn't need any instrumentation. But this needs. So the point in there is that this is typically done for moths and other materials which are not then soluble anymore when they are formed. So we have to form them, the complex in situ, and crystallize in situ, and then get it out from there. And this is the thing. So the sample is placed here in this kind of, this is a Teflon tube, and it's insoluble. All the components what you did, like discussed yesterday, they are all insoluble. You just mix them up. So let's say that you have a component A and component B, and then you have your solvent, and they are soluble. Then you place it in there, you close the cork, you put it inside the steel, what we call a bond. Then you close it, and then you place this in an autoclave. So you put it in an oven. This can be done in an oven also. It doesn't need to be like this. But you need this kind of a safely secured system which tolerates high pressures. So what happens in here is that now when you go and heat this mixture in a closed vessel, clearly up, much higher than the boiling point, it creates a big pressure. So now at the same time you have there in the solvent you have a high temperature and high pressure. That will force the components to dissolve, and then when you cool it down, what you do is you keep it there. You keep it like he was keeping 7 days. You can keep it 1 day or 2 days or so on. But the point is you keep it long enough that all the components are solubilized, and then what you start to do, you start to very slowly cool it down. You let it cool down slowly, and the slower is the temperature decrease, the better chance you have having good crystals. And majority of baths are done in this way. They can be done otherwise, but this is a very neat way to do it. Or some other complexes can be done. Typically metal complexes done like this. But you can also do a chemical reaction. So you take component A and take component B, which are not reacting under normal conditions under that solvent. But if you put it in autoclave, you in a sense force a chemical reaction between A and B happen, and then you cool it down. You will then be able to probably crystallize the product C, which is coming out from it. So this is a very nice technique, both growing crystals, but also making reactions. And it's called a hydrothermal when it's water, and solvothermal when you have anything else. But it needs gear, it needs the instruments for this. You can't do this in our, because it has to tolerate high pressures. And you can see here that it's really a heavy metal, or thick metal container. But it can be done in a normal oven. If you have this bomb, you just heat the oven to like what I was saying yesterday, 120, keep it there for 7 days and then let it cool down. And then if you are lucky, then the crystals have merged here. And these crystals are then ready already. You don't have to do anything. You just pick it up and put it in the diffractometer. You don't dissolve, do anything, because they are formed in situ with the reaction. But now, there are other techniques which are more practical. They don't require any special tools. And there's much more control in here. And these are diffusion methods. So before we spoke about, we always spoke about solvent. We spoke about solvent in a singular form. So using a solvent, the methanol or water and so on, and the other techniques also, either solvent evaporation or cooling down or solvent reactions. But now we take two solvents. And the idea is that if we have this is particularly good for very small amounts of compounds, because what we are doing, this is a nice cartoon of it. We are now discussing the solvent layering technique for this. So we take a long tube, this is a nice thing, and we have two solvents. And now the point in there is that our molecule is dissolved in the solvent S1 now, into which is completely soluble, but the solvent S1 has to be a higher density than the solvent S2, what we put on top of it. And now there is a layer, so there is actually, this is the bottom layer and upper layer, and then we have here the interface between these two layers. And now what happens, this is a very sensitive technique, and it doesn't tolerate at all movement. It's very easy for you to understand, because what we want to do here, and this standard remains calm, but what happens here, this S2 starts to diffuse into this S1. So it means that the local concentration in here, or that local solubility of our target in this area will go down. Because it's not soluble, our target is not soluble in S1, but it's soluble in not S2, it's only soluble in S1. So now we change the local concentration of our solvent in there, so it wants to crystallize. It doesn't want to be in here, in this area, and any other than crystalline form. And this is a very nice technique, but it's rather slow. This might take weeks or so, depending on how weakly or how quickly the S2 diffuses into S1. And this is a very nice technique. I know that Makoto Fujita has used that a lot in crystallizing moths, for example. And that is really nice. And then the idea here is one example. Dichloromethane, diethyl ether combination. So they are heavier and lighter, and then super different. And then, of course, you have to close the vessel, because if you don't close it, it will evaporate. But that is a very nice and neat technique. But this requires a really skillful person, because you have to be very carefully layering this solvent, this S2, on top of that. You should not mix it here at all, because it will precipitate the compound. But that's a very nice technique, especially if you are not in a hurry and you can leave it for 1 month or 2 months in a nice place where there is no shaking. This is another version of the same thing. The idea is that is the idea that you place your molecule in a solvent, like solvent number 1 here, and then you close it with a cork with a small hole. And then you merge the whole thing into another solvent and a closed vessel. And that's what happens through the small hole. The two will diffuse there. And then the local concentration in here will change. So this is a little bit easier technique. And it's called, this is the solvent diffusion. And that's the idea in there. That's the very simple thing to do. And this is much more easier in practice than a long tube. But the long tube often offers better nucleus sites in there. It's like an enema tube. When you evaporate an enema tube, it's a very nice. Nobody can really tell why is this. Maybe that is the movement of the solvents, and so local concentrations are more concentrated in the small tube. But that works fine also. It's a very simple technique. And now, convection. So this is a tool. You need this kind of instrument, and the idea is this is available as a class, this kind of a reversed A. And the point in there is that this is also a cooling method. That what you do, you actually have your sample here, and it's not soluble here in the native temperature. So it's now insoluble in here. But what you do, you heat it up here and there, so that part of the thing is warm, so it starts to rotate there. So there will be a current flowing, or convection flowing on this direction. So it will take here this part, solubilize your compound, it goes in here, and it comes in this part, and now there's a cooling. So we cool this part of the solution. And this cooling, it's like slow cooling, then it induces precipitation or crystal growth, if we are nice, and then the crystals drop in here. And then when everything goes fine, because they travel with the solvent in here, and the crystals are there. Now, something explodes. But you can hear me. Now we out from here. Yeah. Run out. Okay.
Yeah, it's me.
Yes, I can.
Hello.
Yeah. Okay, it works. So we will do it now, like this. So that's the it's a tool what you can have. You can use this kind of a tool for this, and then when you have done enough and crystals emerge here, then you can then separate them, pick them up from here, and put it in the diffractometer. I've never personally, or my group, have never used this. But it's, in some cases, it's quite convenient and easy, again. And the point in principle is closed, again, that there is no evaporation. It's just cooling, this kind of a controlled cooling. And this is a rather nice thing. But then the method, what we use, let's say 90% of all the time, is vapor diffusion. And this is a very practical technique to do this. So it's a little bit more demanding, of course, than the slow cooling or slow evaporation, but it's nearly as simple as it is. And it's very easy to do. So it works like this. So the point is that you have again a solvent S1 where your compound is completely soluble. Remember, that's why the solubility profiles are really important. And then you place it in a tube like this. It can be open or it can be like this, that there's a cap and some holes in here. It can be open. And then you have another solvent here, S2, but now the vapor pressure of this S1 should be lower than the S2. So the S2 will create here, this is a closed one, it will create a gas phase, and now this gas will then go in here and slowly diffuse in here, and now this level will go up because all the time there's S2 going into S1, and then the concentration, so the solubility of our target molecule will be smaller and smaller all the time. And this is a very neat technique because it's closed, you can see, and this is a real light. So this is about 3 centimeters, 4 centimeters. So you can see there is a cap closed bottle. Inside that there is a small one, there is no holes, it's open. There is a yellow S1 solution surrounded by S2, and now in this area here the crystals are growing. This is a very good technique in many ways, because the point, everything is closed, there is no evaporation. If you use open or these kind of, not open but clear vessels, you can see what happens by your eye. So, okay, yes, that's that. And once you see something happening, or even sometimes you might create colorless crystals which you can't see by your eye. So it's very simple. You open a cork, you close this cork, and then you go to the microscope and look, okay, there is some crystals already now there, and then you keep the cork closed, and then you pick up the crystals from there. Or if it's not, you can open the cork and put it back. And this can bring you crystals, I would say, within 1 day, 2 weeks or something like this. But it's really nice and safe. You can just leave them, you can make many of them, and you can just take a look, each of them, okay, this looks that there would be crystals in there, I will check them. But this is a very, very good technique to do this. Then there's more techniques which are useful, and very good ones, also in many respects. Also, you can do reactions with it. So if you want to create an inorganic complex, a metal complex, or this kind of a normal coordination complex with a metal and ligand, this is a very neat technique to do this. So it's called the reactant diffusion. But for that, you need so-called U-tube. We know what the U-tube is, but this is a different U-tube. So the idea is that we place here at the top, at the bottom of the U-tube, a gel. It could be silica gel, or in principle any gel which tolerates these 2 solvents. So of course the gel has to be something that it will not be dissolved by this solvent. So what we do in the red solvent, we can have our molecule, or we can have a component, like here reactant A, and then on the other side we can have the other solvent which is our compound is not soluble, or we can have a reactant B. And then we just let them be. We'll close this normally. Of course, we don't want to have an evaporation. And now what happens? That this red reactant A starts to diffuse in this direction, and this reactant B starts, and here in this region where they meet, the crystallization happens. And this is a really, it can also call that the gel crystallization. So it can be, it's a really good, I know one of my colleagues has done a lot of pharmaceutical morphological studies using gel crystallization. By modulating the solvents and the gel itself, you can induce something happening. Just consider that you have a chiral gel. Then you have a chiral environment. This is a really nice way of modulating the system during these changes and seeing what you can get out. And that is a very nice thing. And then get used to, especially for metal complexes, this is a very convenient way to do this. And now, if you are working on a charged systems, so you have a metal complex, for example, or organic cation that has a positive charge, we have an additional variable in addition to everything what I've shown. That is the anion. And now it has a big impact. So the anion can be the key on what it crystallizes or it doesn't crystallize. So that is also the idea that you have to think very carefully which kind of anion you are using if you want to have a crystallizing single crystal from a charged system, so salts. And the same applies to reverse. If your system is anionic, like these MOMs are, metal organic frameworks, of course, can be, but also these metallics are typically anionic. Then it plays a crucial role which kind of a cation you're using. And that can change everything. But that leads us more possibilities. So you can have 10 different anions. Everything else remains the same, but you just have it chloride, bromide, iodide, triflate, sulfonate, whatever kind of a thing, even very large ones. And that might help. Again, nobody knows in advance. So you have to make a testing, you have to test what happens and so on. Sometimes you're lucky, the first thing works and so on. Or if you have a cationic system, so that is a different kind of a thing. PF6 is a very nice non-coordinative anion, because if you have a metal complex, sometimes you don't want to have the anion to be coordinated with your metal complex, so you need a non-coordinated. And then if you have an anionic system and you want to crystallize it, when you use alkali or any metal cation, it will coordinate to your anion in a solid state, that's a bad thing. So then you use non-coordinating cations like TMA. So you get, there's a really big modulation possibilities when you are working with non-molecular systems, so charged systems. So with the ionic is like molecule, because it has a positive and negative charge in there itself, but it also can help sometimes that the charges will interact and then it will create a nice crystal. Now, there are ways to do also other things. So you can start to play the hard game, and the hard game, yes, please. That's fine. Okay, thank you. It's better. That we can play risk. The other methods what we have been discussing now always rely on a pure system. The pure means that we have one target and we do everything to get this one target on crystallizing, making the crystal. But it might be that everything what we have done doesn't work. We have done 50 experiments and always fails. Either we don't get any crystals or we get powder or whatever. So then we might try, depending on the system, we might try of adding something. So making it deliberately impure. And then we are talking about co-crystallines. So we add a component B. So we don't want to, let's say that we have a component A, it doesn't crystallize, whatever we do. But then we think about it, okay, maybe if we add a component, a molecule B in there, and crystallize them together, if they make one-to-one complex, and this complex then crystallizes. That is a chance, but there is a big risk, because at the same time you make it impure. So now the B might even disturb it more than it was by itself. But that is something like this. So the idea is that we call it crystallization aid, and this is, it's also, I have many cases like this. So that we had component A, we tried everything, 50 different tries, no way, no crystal. Then it's okay, let's try to do this co-crystallizing things and add another component. And we thought, okay, maybe there is, let's say, hydrogen bonding or pi-pi interaction or any kind of additional interaction between these components. We did it, and it turned out to be yes. Okay, we were lucky. We got 1 to 1, so there was a volt A and B in the crystal structure, which was there. So at the same time, we got the structure of our target molecule and then the component B. But it can also happen so that the B induces crystallization. So the actual idea is that you put it in there, but it doesn't come. It makes the crystal, but it doesn't come with the component. And this is really amazing. So it's the B acts like a catalyst for the crystallization. And we have had a few of these kind of cases that's the case. Also, it can be sometimes with the solvent, that you dissolve your compound in a solvent, you crystallize, whatever method. It might be that solvent comes with your compound, because it makes a better crystal lattice with the solvent without this. Or it might be so that it is there, but it doesn't crystallize. The molecule by itself crystallizes. We never know this in advance. It should not be a big surprise that, okay, there is a solid molecule. But it can be also another component. And of course, if you have a cationic species, then that's the anion is the B component. Changing the B might change everything, or if it's the other way around, then you change the cation. Because you cannot separate them. But in the molecular world also, if you have a neutral molecules, it can be done. But it's a high risk that you will not get anything. But that's the idea. And then, if you are working in water, you're going to change the pH. And this is a typical trick for you have a very complex amine, for example. And then you try to crystallize, it's always an oil. You don't get it, always it comes as an oil. So the easy thing in there is add, let's say, hydrochloric acid or hydrobromic acid to make a salt out of it. So you protonate the amine to make an ammonium cation, and then you have a salt. And salts, by default, always crystallize better, 99% of the cases, than a non-charged system, because you have electrostatics there. So that's a trick. So you still have the compound, but now it's just a protonated form of your compound. That's okay. It doesn't matter. That's the idea. So controlling pH can modulate the thing. You can do it with the co-crystalline, or you can do it individually. So as you can see, we have a huge palette of possible means of growing the crystals. And the difficulty that we never know that in advance. So that is the idea that if I get a sample from somebody, I can only say, okay, I will do my best, but I can't promise anything. The only thing I have to do everything from the beginning to the end in order to see how it works. We are always lucky and when we see the single crystal coming out. Okay, now we got the most difficult task is done, then go to the diffractometer and do the measure. That's the idea. We can also do this seeding, crystal seeding, so that sometimes helps that you add a tiny crystals in the saturated solution of your thing, that seeding can help, that induces. So it's like a kick for the process. We have never used this because our systems are too complex, but this is being used in some pharmaceutical and industrial crystallizations. You see it in sugar crystals normally, when you crystallize sugar, normally they use this seeding for this. And then a couple of very unique systems is sublimation. So you can actually do, it doesn't normally work to anything else than purely organic compounds, is the idea is that you need a tool again. So your compound is here, you draw a vacuum, that the whole system is in vacuum, then you start heating it up. So actually what you do, you vaporize your molecule, and then you have here a cold finger or something, and then the crystals grow on there. Because that is also a temperature gradient based thing. But you can easily imagine that your system has to be volatile. So it has to be able to go to the gas phase without destroying itself. And we normally use the high vacuum for this. We have done this a couple of times, but it's a very, very complicated thing in general. Okay, we are closing down soon. The growing protein crystals is a special technique, And the idea is just show you briefly, so it's a hanging drop method. So you use this kind of a thing, and you have here protein crystals in a very low concentration inside your droplet, and here we have the reservoir. So that's the idea. There's also a concentration change happening in a droplet that causes this. Or you can have a standing droplet. So in principle, this is the same thing, but it's always inside. But nowadays, this was the classical way of doing this, but nowadays it's done on a plate, typically a 96 well plate, that each of them, in principle, in the best case, will grow one crystal. But we don't use this technique. It is because this is for huge screening, so you have to do hundreds of thousands of experiments on that. And that's the idea how the protein crystal recovers is doing. There are even instruments we can read this, is there a crystal or not. But in our case, we normally use our eyes and do it like this. Now, here are examples of crystals. This is a nasty case because there are two different crystals. We call it twin crystal, and in here you can see also, now you can see what happened when we use polarized light, that this is clearly not a nice part. It's crystalline, but it's bad. But there seems to be a nice place. So this is a single crystal, this is not. And you can see the crystals can have all kind of shape and sizes and so on, but they never know if the crystal is good or not. So this good looks nice. If I see something like this, I guess, okay, yes, that looks like nice. And if you want to see nice crystals, if you have a table sugar, white table sugar or salt, these are very nice crystals. If you just put them in a black paper, you can see from your eyes, they're very nice cubes. And they are both excellent crystals. So this is just examples of how polarized light can show us things. So if we have a good crystal, then it will shut down in the polarized light. When you use the polarized light in certain direction, it is killed. So it means that we have a continuous lattice in there. And again, some examples: good crystal, bad crystal, we can't be sure, certainly not a crystal, and so on. And this is actually the idea that they can be, this could be a good crystal or not. I'm sure this is certainly nothing. This is a cracked crystal. It was okay, but it was taken out from the solution, then it cracks. We can't use this, of course. Very nice looking. Here might be, you can see a little bit soft on the sides. We can't be sure it's okay. But we can't tell that in advance. How we attach the crystal then when it's done into the diffractometer? We need a sample holder, and this is a sample holder. And if you would be in my course, in my university, we would go to the instrument, and then I would show you what it is. But this is roughly, this is what, in this case, I think 200 microns, so 0.2 millimeters, so it's really small. You have to, this is on the microscope, the instrument has a microscope. And that was last part of this, so this is what we are doing. We grow the crystals, we put it in this kind of a sample holder, and then we place it in the diffractometer. And then the measurement is completely different. We can't actually do this in this course, it's not needed, because what we now do with the next, we will jump from here to the phase. We have done the measurement on a good single crystal, how we can get the structure out of it. And this is what I'll show you in the next lecture. And now we are 2 minutes overtime, so we can have a short break of 5 minutes.